have to wait for the camera to roll, and then there's some startup time there. Okay, we are ready. Good afternoon, everyone. It is my pleasure to introduce our colloquium speaker today, Dr. Jeff Nicholson. He is a distinguished member of the technical staff in OFS Laboratories. Dr. Nicholson received his bachelor degree in physics from University of Houston, Texas, so it's nearby state, so not far from us. And then Ph.D. degree in optical sciences in 1991 from University of New Mexico. 97? Okay, sorry. So in 1997, he got his Ph.D. in University of New Mexico, also from a neighbor state. So it's great that he's here with us today. And you actually came from the same group with Jason Jones, right? Who is our faculty member here, so it's a great group because we have Scott Didams also from there, right? Who also gave a colloquium here not a long time ago. So after the PhD degree, Dr. Nicholson went to work at the Los Alamos National Laboratory in New Mexico on femtosecond punch propagation and characterization. And then he moved to the directed energy solution in Albuquerque and worked in the area of high-power mid-infrared gas lasers. So that is still an interesting topic nowadays, I think. And in 2001, he moved to Lucent Technologies Bell Laboratories, so that Bell Labs, in New Jersey, to work in optical fiber research group. Bell Labs was sold to Furukawa Electric later, and then became OFS Laboratories. So he was telling me that the first price, the same price was $12 billion for that portion, and then it kept going down, and then at the end it was sold for $1 billion. So it's an interesting dynamic there. So his current research interests include high-power fiber lasers and amplifiers, Raman fiber lasers, high-order mode fibers, and hollow core fibers, and nonlinear propagation effects in optical fiber. So he's going to talk to us about application of few mode optical fibers today. So let's welcome our speaker.
Thank you, Ron, and I'd like to thank you and the Colloquium Committee for inviting me out to give this talk. Hopefully today I'd like to give you a flavor of some of the work that's going on in few-moded optical fibers, which is an active area of research right now. And before I go on, I just want to mention that this is the work of a large group of people at OFS, covering everything from the design, fabrication, draw fibers, and then the device aspects as well. So it's not just the work of myself. Just to give you a brief background on OFS, as Con mentioned, the Optical Fiber Research Group was spun out of Lucent and Bell Labs in 2001, and we were bought by Furukawa. We have about 1,500 employees, and we're the #2 worldwide in fiber manufacture and #1 in specialty fiber. And we have locations all over the world. I'm based in Somerset, New Jersey. And we cover the specialty fiber division covers all the markets where fiber can come into play. So OFS's big product is in the telecommunications market, but the specialty market covers medical, fiber lasers. Fiber lasers is the big application area in our location, and then applications in government, aerospace, and defense, and in the industrial market as well. And at OFS, basically, we take in the raw materials, glass tubing, chemicals, and then walk through the whole process of fiber manufacture. So from fiber design, preform, drawing, cable assemblies, devices, everything. So we start with the raw materials, and out comes the fiber laser. So now moving on into the technical part of the talk, here's an outline of what I'd like to present. First, I'd like to talk about single-mode fibers and some of the design limitations that come about when you want to really think about specialty applications and limiting yourself to single-mode optical fibers. If we're going to open up the design space from single-mode to multi-mode fibers, we have to be able to measure precisely the types of modes that we're generating in our optical fibers. So I'll spend some time on that. And then I'll talk about two of the application areas which we're heavily involved in. One is in hollow core fiber, and then the other is very high performance fibers for fiber lasers. So just to say a few words about the fabrication process of optical fibers, we start with the preform fabrication, and there are any number of ways which one can fabricate an optical fiber. For the sort of telecom and fiber laser fibers which I'm talking about, we use a process called MCVD, or modified chemical vapor deposition. And the idea is that you start with a starting tube, you have your silicon tetrachloride and germanium tetrachloride coming in the vapor phase, and then a torch deposits the soot on the inside of this wall as the tube is rotating. So by varying the level of dopants, you can create the index profile in the preform that you want. And then when all the dopants are laid down in this tube, you finally collapse the tube into a solid rod to create the final preform. Then the next step is fiber draw. And the basic point here is that in the telecom world, people talk about drawing megameters of fiber. And to do that, you really have to have very large towers and very high draw speeds to make everything economical. So the height that you need to build to is dictated by how long it takes to cool the fiber as it's drawn here. And so then we draw it, and then after it's cooled, we apply a polymer coating, and we have feedback control to ensure that the dimensional control is very precise. And as I was saying, for telecom type single mode fibers, we will draw hundreds or thousands of kilometers of fiber. So this is now a closer look at a step index optical fiber. And in a single mode fiber, we might have an 8-micron core, which has a high refractive index, and then maybe a 125 micron cladding. And in the ray picture of light propagation, the guidance in is by total internal reflection. And so this is this basic propagation method, but it's perhaps more illustrative to look at a modal picture of propagation in optical fibers. So in order to propagate the modes, you look at the wave equations, and then you impose the boundary conditions of your refractive index profile. And one of the common approximations is that we have a small delta here, that the difference between the core and the cladding index is small. And when we make that approximation for step index fibers, then you can come up with analytical solutions for these fibers. And the analytical solutions turn out to be Bessel functions. And in this approximation, the modes are linearly polarized, and so we call them the LPMN modes to determine the order of the mode that we're talking about. And so, for example, the fundamental mode, which is illustrated here, is the LP01. And then the first higher order mode would be the LP11. So these electric fields are illustrated here. So in telecom, much of the work is single mode, and one can pretty readily arrive at this expression which tells you what you need to have in terms of the refractive index profile to achieve single mode operation and fully suppress all of the higher order modes. And that basically depends on this number A, which is the fiber core radius, and the difference in core and clad refractive index. So let's, single mode fibers have been extremely successful. We operate now with a loss at less than about 0.18 dB per kilometer. And you can see that's very near the theoretical minimum. So a lot of work in the telecom world now is people fighting about this last 0.005 dB per kilometer of loss, trying to drive it down just that little bit of extra step. So it's extraordinarily pure material and very close to the theoretical minimum. But the point is that while that's great for telecom, as you move into the specialty markets, requiring single mode operation constrains the sort of fiber designs that you can achieve. And I'll give you a simple illustration as to why that is. So in the high power fiber laser business, you're often fighting nonlinearity. And in order to reduce the nonlinearity, you want to make the core of the fiber as large as you can, because that lowers the peak intensity in the fiber and reduces the nonlinearity. So if we look at this single mode criteria and say we're operating at a wavelength of 1 micron, you can very easily plot as a function of core radius the difference between core and cladding index that we need to achieve single mode operation. So as we go to large core, we need a smaller delta N, which is fine, except that there are fabrication limits to how precisely we can fabricate a refractive index. So those fabrication index fluctuations tend to come in order of 10 to the minus 4, which means there are very practical limits on how low you can drive this delta. Now, obviously, it's not a hard and fast line, but it's easy to imagine that as the refractive index fluctuations get larger than the delta that you're trying to achieve, you no longer have the waveguide that you're trying to design. So in this very simple step index model, the tolerances fiber fabrication limit the practical size of single mode fibers that we can make. So that's one limitation of single mode fibers. But the other thing is, if we open up the design space to higher order modes, we can achieve new functionality. So this expression here is an integration over the intensity of a mode, which tells you what the effective area of the mode is. And the important thing to keep in mind is, if you have a waveguide that supports multiple modes, the waveguide area is the same for all those modes. But the electric field and the intensity profile is different. And as a result, higher order modes and fundamental modes can have very different modal effective areas, even though the waveguide area is the same. So to give you an extreme example of this is a waveguide that we actually have developed at OFS, which has a center core and an outer core. And the fundamental mode, because of this peak in the center, is confined to the center. But a higher order mode utilizes the whole waveguide. So they both have the same waveguide area, but the higher order mode has a huge effective area and much lower nonlinearity than the fundamental mode. So the nonlinear properties of higher order modes can be very different than the fundamental mode. At the same time, as I showed you, the higher order modes sample different regions of the waveguide, which means that the propagation constant, which is a function of both the material and the waveguide dispersion, can be very different for higher order modes, because the higher order modes have very different waveguide dispersion. So here I'm showing the Taylor expansion of the propagation constant, breaking it up into the first term, which is the group velocity related to the differential group delay, and then the group velocity dispersion. So again, an extreme example of this sort of waveguide dispersion control is shown here, where we have a very complicated index profile. But the point is that the LPO2 mode, now because of the ring structure, extends into a waveguide area that the fundamental mode doesn't sit in. And as a result, the LPO2 has very large positive dispersion, anomalous dispersion at 1 micron, which is very difficult to achieve in a single mode fiber. So both the dispersion and the nonlinearity of higher order modes give us an extra degree of freedom to play with. So, few-moded fibers, they open up the design space, and it turns out they're an active area of research in a number of different application areas. One that I won't talk upon today, but is very active in the telecom world, is spatial division multiplexing, because the notion is that we're running out of bandwidth. So by allowing a fiber to have few or multiple modes, we can send an information channel on each optical mode and increase the information capacity of a single fiber. That's a very active area of research. What I'll be focusing on is developing novel sensor fibers and fiber lasers for high power and pulsed applications. So this is great. We can use higher order modes that have new functionality, but we have to be very careful, because if we're not careful, bad things happen. And a number of these bad things can happen. So the modes in the optical fiber are coherent. They have very slow walk-off, which leads to coherent interference between modes. That leads to spectral modulation. It can lead to pointing instabilities when the beam exits the fiber. If you have pulsed applications, the modes have different differential group delay, so they can walk off, and you can put in a single pulse and get multiple pulses out. You can add relative intensity noise or cross-mode nonlinearity. So there's a number of effects that can come into play. So to mitigate these effects, we have a couple of different design strategies. One strategy, which we apply in our sensor fibers, is to say, okay, we'll let this fiber have a core which contains multiple modes. But now we're going to add extra features to the fiber to increase the differential loss of the higher order modes. So even though they exist in the core, they're strongly suppressed. The other strategy is just say, okay, we're going to treat this fiber extremely carefully. We're going to design this fiber that supports multiple modes, but we're going to design it the waveguide in such a way that they don't couple together. And we're going to be very careful about handling and launching into the fiber to make sure we very cleanly excite a single higher order mode. So with that background, before talking about the applications, I'd like to talk about how we measure these higher order modes. So let's start with, again, the LPO1 and the LPO11. And keep in mind, the walk-off of these modes is very slow. So for all practical purposes, in fiber lasers, for example, these things are fully coherent. When they're fully coherent, if you launch a broadband source into the fiber, you get beating due to the walk-off of the modes. And that spectral beating is related to the frequency of this beating is related to the inverse of the group delay difference between the modes. And the amplitude of the beating is related to the relative power between the modes. So we can do a Fourier transform of this, and then we get a picture showing at what differential group delay we have between these modes. So this tells us the walk-off between the modes. But the picture is slightly more complicated because the spatial properties of the modes are different. So for example, if you imagine you're sitting in the center of this beam here, where the LP01 is at a peak, there's no power in the LP11. So if you look at only that portion of the beam, you should see absolutely no spectral beating. And the spectral beating is actually maximized up in the wings of the beam. So that's the key to how we measure that. The other thing you have to keep in mind is that the modes of a waveguide are orthogonal. So if we take that whole beam that contains an LPO1 and an LP11 and look at the electric fields, and we put that beam on a square law detector and integrate over the whole beam, we'll measure the intensity of the 01 and the intensity of the 11 in the cross term. But this side of the LP11 and this side of the LP11 are out of phase with respect to each other. So they integrate out. And if you detect the whole beam, you actually lose the entire interference term that we're trying to detect to use the measurement in order to measure the modes. So what we need to do is do some spatial filtering. We'll filter out most of the beam and detect only a small part. And that gives us the interference term back because we've broken the orthogonality. So that's the basis behind this measurement technique which we've developed at OFS called spatially and spectrally resolved imaging. And the idea is we're just going to do spectral interference, but we're going to spatially resolve it in order to get around the orthogonality of the modes. So we start with a broadband source, launch it onto our fiber under test, and then image that output onto a single mode fiber. And the idea is that we connect that single mode fiber to an optical spectrum analyzer and measure the spectrum. And then raster scan and measure the spectrum. And then, so we just raster scan over the whole beam and get a data cube which corresponds to position, x, y, and wavelength. And you can see as we build up that optical spectrum, what we're really doing is we're measuring the beam profile as a function of wavelength. So this is how the measurement was first performed. But nowadays, we just directly use a tunable laser and a CCD to measure this beam profile as a function of wavelength. Either way works. In the end, you end up with the same data cube. So now you've got this data cube. What do you do with it? So what you do is you analyze the coherent beating of the modes on a per pixel basis. So you pick a pixel, and there's the spectrum that we measured from our single mode pickup fiber. And you do the Fourier transform, like I said before, and that gives you a couple of peaks. These peaks each correspond to a different mode beating with the fundamental. Then after a little bit of data analysis and some Fourier filtering, you back out the mode intensity that corresponds to this differential group delay. And you can do this for each peak that you see in the Fourier transform. And by doing that for all of the pixels, you then build up a picture of the higher order mode and its relative power. So let me just say a little bit more about the data analysis. There's an assumption here. We assume that we have two modes, and we assume that one of the modes is much stronger than the other. So it's all the other weak modes are beating against this strong mode. And what we want to calculate is the relative power between this weak mode P2 and this strong mode P1. When we take the log of that in telecom world, they call that MPI, or multipath interference. But basically we're just integrating over the intensity, the spatial distribution of intensity between the two modes. So we have our Fourier transform, and at each pixel, if we put a Fourier filter around the DC component, it's fairly easy to show. If you integrate that DC component with respect to the filter, then you just end up with the strong mode. So I1. Then we put our Fourier filter around the peak that corresponds to the beat note between the modes, and again, you end up with a fairly simple relation. Once you know I1 and the filtered intensity, you can back out the mode number 2. As I said, the most important assumption that goes into this is that we're assuming one dominant mode and many weak modes. So let's see what this procedure gives us in a real optical fiber. So here we're starting with a 30 micron mode field diameter. So again, to go back to telecom world, a single mode fiber may be something like 80 micron effective area. This is 700 micron squared effective area. So this effective area is 10 times larger than a single mode fiber, and it has a lot of modes that it supports. If you look at the beam profile, you see this very nice round beam profile. But if you look at the beat notes, you see a lot of things going on in here. And if you do that Fourier analysis on each of these beat notes, now what you can see is each one of these corresponds to a different mode of the waveguide. And you can see where the relative group delays come from and their relative power levels. So this is a very powerful tool because we've separated all these modes in group delay and pulled out their relative powers and gotten their spatial profiles as well. So that's S squared. I'd like to talk about a related measurement that we do where we just look at high resolution transmission to build up what's called a spectrogram. So this is related but slightly different than the data analysis that we do in that we just launch a narrow line width tunable laser through our fiber that we want to look at and measure the transmission of that fiber. When we do this, we get this very noisy spectrum. Again, this is because of the beating of all the modes. So if you took a Fourier transform of this entire spectrum, you wouldn't get a whole lot of interesting information. But if we slice up the spectrum and do a Fourier transform, and then slide our window over and do a Fourier transform, and slide the window over and do a Fourier transform, we build up this map here, which is called a spectrogram. And what we're doing is basically resolving in both wavelength and group delay now the higher order mode content. So each of these lines now, these bright lines, is the movement of higher order mode in both wavelength and differential group delay. And you can see a complex wavelength dependence to the mode content now. So we take the spectrogram, and now we add in the extra measurement of the mode images that we can do with S squared, and we can build up a full picture of the mode content in these few mode fibers. So this particular fiber that I'm showing you here is a photonic bandgap hollow core fiber. And there's some low loss windows here, there's high loss here, there's low loss here. And bandgaps, they just have this very rich mode content that's going on. You see, you often see these sort of S-shaped curves related to moving to the edge of the loss region. And so again, it's a very complicated picture, but we can pull out all this rich mode information with these coherent measurements. Finally, because it's coherent and because we're doing Fourier transforms, we can track the phase of the Fourier transform as well and actually build up phase images. So again, the LP11 has these pi out of phase lobes, and we see a pi phase shift in the Fourier transform when we back out and do the data analysis. We can see the pi phase shift between the center lobe and the ring and the LPO2. We can go up to very high order LP17s and see them alternating in phase around. So it's very nice pictures. So that's how we measure the modes. Now I'd like to talk about using these measurements in our development of the single mode hollow core fiber. So I showed this picture before. This is conventional optical fiber with light confinement using total internal reflection. Band gaps are completely different. So hollow core, I should back up and say, our focus at OFS has been photonic bandgap fibers, because these are the fibers that have the lowest loss in the dB per kilometer range. But there are many, many other types of hollow core fibers that are being actively investigated right now for various applications. But I'm going to focus on bandgap fibers, and in bandgap fibers, the guidance mechanism is completely different than conventional fibers. So we imagine we build up a 2D array of a regular lattice, and then when we have a bandgap, light at certain wavelengths can't enter that lattice in no matter which direction it comes in. So what we do is we create a defect in the center of the lattice. We pull out some of these rods to create a core, and then light that launches into the core can't get into the cladding due to the bandgap. And that gives us our guidance mechanism. This is great because we now have light propagating in air. We can have very low nonlinearity compared to conventional fibers, and we can potentially have very low loss. But almost all hollow core fibers out there support a lot of higher order modes. So to show you what I mean by that, this is a fiber we made at OFS. It has about 5.9 dB per kilometer loss, so it's very low loss. But it has an enormous amount of higher order modes. So we can add, that's our spectrogram, we add the S squared data analysis to it. And we can pick out LP11s, LP02-like modes, even very higher order modes. There's lots of mode crossings going on here. So it's a very complex picture. But all of these modes are clearly visible, well guided, and we can't bin them out. They're not bin sensitive. So they're there to stay. So why do they matter? Because of modal interference. This, for example, is the beam profile that you get out of that fiber. All those modes beat together and give you strong distortion in the mode profile. But a lot of applications will benefit in hollow core from having single mode and perhaps polarization maintaining. So high power laser delivery, femtosecond pulse compression, using these for telecom applications, all of these things would benefit from single mode guidance. So how do you get rid of the modes in these fibers? Well, one strategy is well known. You just reduce the core size. This is sort of the photonic band gap of the V number. We just reduce the core size, make it smaller, it becomes single mode. So when you remove 19 of these lattice sites for a 19-cell core, we have something like 40 or 50 modes. When you go down to a 3-cell core, we end up with one mode, which is great, except there's a trade-off. When you make the core in a hollow core fiber bigger, the loss comes from scattering at the glass surface. So when you make the core bigger, the light stops interacting with the glass surface. And that's what we need to do to get the loss down. So with this large core, you have very low surface interactions, which is great because it gives you low loss, but it gives you multimoded and perhaps low birefringence. Make the core small, you have very high surface interactions, which increases the loss and also the nonlinearity because now you have a lot of light guided in the glass, but you get the single-moded and high birefringence. So there's this natural trade-off that you have to fight with when you want to get single-moded and low loss. Our goal is to get rid of that trade-off and have these very large cores that are still single-moded because we need to get down to single-moded in the few dB per kilometer range. So what's our strategy? Well, as I said, we start with a core. Make it few-moded, but then we add structures to the cladding. So what we're adding here is a second shunt core. And if we design the shunt core just right, we can induce resonant phase matching between the center core and the shunt core. So here is the index of the fundamental mode, and it's sitting up here all by itself. But the first higher order mode is resonantly phase matched to the fundamental mode of that shunt. And so there's very little barrier for that mode to tunnel into the shunt and then on out and out of the fiber. It turns out that a 19-cell center core and a 7-cell shunt core very conveniently give you this sort of phase matching that you want. So that's the structure. And we looked at a little bit of modeling of this structure. So we've got our center core, 19-cell, 2 shunt cores. And here I'm showing some index calculations of the modes. So blue is the index of the fundamental mode in the center core. Green is the index of the fundamental mode in the shunt core. And then red is the index of these higher order modes which we want to strip out. And we've designed this structure just right. We have very broad wavelength range over which the index of the fundamental mode of the shunt and the higher order mode of the center core match, and those things just go away. Except, again, fabrication precision kills us. Any small deviations from that ideal design moves these modes up and away from the shunt core. So when you look at this, the first thing that you would think is that the design won't work. It's too sensitive to fabrication. But it turns out there's post-processing that we can do to this fiber after it's drawn. And that post-processing that we can do is we can bend it. So imagine you have this fiber and it's wound helically in this way. And here are our shunt cores and our center core. And the effect on the mode matching depends very sensitively on the alignment of this shunt axis with the axis of the bend. So for some alignments, there will be zero bend perturbation. We'll have this index profile, and the shunts won't be index matched with the center core. However, if this is oriented differently with respect to the curvature, when you bend an optical fiber, you tilt the index profile. So at some bends, this mode will move up and this mode will move down. We still don't have index matching. But at other bend orientations, this mode moves down, this mode moves up. And at just the right bend orientation, we have index matching. So it turns out perturbations that we induce in the fiber due to bending it intermittently cancel the phase mismatch caused by design imperfections. So what's that do to this fabrication imperfection picture? Well, it takes this green shunt mode, which in a straight fiber looks like a very narrow line, and broadens it out and gives us a very wide region of resonant phase matching now. So that bend gives us this, compensates for the fabrication imperfections and broadens the resonance region. And it turns out that when you bend this fiber, you can get LP11 modes whose loss is 2 orders of magnitude higher than the fundamental mode at some wavelengths. Not at all wavelengths, but at some wavelengths. So we call this effect, where we post-process the fiber with bending, a perturbed resonance for improved single-modedness of prism. So again, to say a few words about how we fabricate these fibers, again, the preform fabrication is completely different than MCVD fibers. Now we use a technique called stack and draw, where we draw a number of capillaries, we stack them into this regular lattice that we want, we draw, and then we overclad it and end up with a preform. We draw that preform down until it's a few millimeters in diameter, add some more glass to the outside of it, and then draw it into the final fiber. This is what the fabricated fiber looks like now. So again, 19-cell shunt, 7-cell center core, and very high airfill fractions. And this is the loss that we measure on 200 meters. The minimum loss that we get is about 7.5 dB per kilometer. What's interesting is to look at the spectrogram and the S-squared measurement. So here I've got that reference 19-cell fiber spectrogram that I showed you earlier with modes crisscrossing the entire low-loss region of this fiber. Here's the spectrogram of the prism fiber, and you can see already a greatly decreased mode content. So we really only see the LP11 and a couple of LPO2s. And so we already have low HOMs in this straight prism fiber. And if you think back to that section where I talked about the effect of bending in the prism fiber, we naturally expect bend sensitivity to these modes as well. So here's the spectrogram as I take a straight fiber and then bend it to progressively smaller and smaller coil diameters. And you can see these fingers corresponding to the LPO2 shrinking back until when we get down to around 4.5 centimeter coil diameters, we have a region which is entirely free of HOM contact now. So the bending induces large additional HOM suppression. So let's go back to this picture of the beam profile now. Again, here's the reference fiber, and here is the beam profile. Remember, I told you that S-squared was building up a picture of beam profile versus wavelength. So what I'd like to do is show you the S-squared data as a movie. This is the data that we take for S-squared. And this is what happens to the mode as the phases between the modes change when we adjust the wavelength. You get this sloshing around and strong beam distortions. This is what happens in the prism fiber when we do the same S-squared measurement. It effectively looks like a single mode fiber now. We've removed all of these perturbations that caused by the higher order mode, even though the core design of these two is roughly similar, and in principle they support the same number of higher order modes in the center core. The strong shunt cores suppress all of those. We've recently taken the next step, which is to add more functionality, and what we're doing now is we're deliberately adding asymmetries to the core walls here. So we may add some thickness, some areas to the core wall to increase the thickness at specific locations. When we do that, we can look at an unpolarized cutback, and we see very similar features. We see some low loss regions, but things look much more interesting when we look at the polarization properties of this fiber. So now this fiber is being measured on 500 meters of fiber, and we're seeing two loss windows. In one loss window, we see practically no polarization properties. But in the other loss window, we see very strong polarization dependence between the two axes. And in fact, the minimum loss of this low loss axis is less than 5 dB per kilometer. And we have 26 dB per kilometer of polarization dependent loss. More impressively, after 500 meters of fiber, we can measure polarization extinction ratios of better than 30 dB, which means we have H parameters of 6 times 10 to the minus 6. So these polarization holding properties compare to conventional standard PM fibers now, except it's hollow core. So that's all I want to say about hollow core at the moment. Now I'd like to move on to our fibers for fiber lasers. And this is the second design strategy that I talked to, where we're just going to allow the waveguide to support multiple modes and treat it very carefully and design it so that mode coupling doesn't occur. So the name of the game in high power fiber lasers is to reduce nonlinearity. So we got to reduce nonlinearity, so we increase the power. And there are any number of strategies out there to increase the mode area and to decrease the nonlinearity. For example, rod-type fibers are very successful. They produce very high peak powers, but the downside is you've moved more into a solid state regime. These things have to be held straight. They're a meter long. They've decreased the delta of the refractive index to the point where they're too bend lossy. They can't be bent at all. There are other strategies where people are adding features to the cladding to strip out higher order modes again, much like we did in the solid core fiber. But all of these approaches are based on operating in the fundamental mode of the fiber, and there are some downsides to this. I'll talk a little bit more about this, but fundamental mode is very susceptible to nearest neighbor coupling. It wants to couple very easily to the LPO1. The LPO1 wants to couple easily to the LPO11. At the same time, as you make this index big, you get bend-induced perturbations to the refractive index. This is that same tilt that I was showing you in the hollow core. Now what that tilt does is it reduces the effective area of the mode. So you design a fiber which when it's straight has a huge mode, but then you coil it and its mode collapses. So at OFS, to increase mode area, we've taken a slightly different approach, which is to deliberately operate now in higher order modes. And there are a number of somewhat counterintuitive benefits to doing this. First of all, it provides scalability in effective area. It reduces the nearest neighbor coupling, and it does this in a platform which we can coil and fusion splice. So the collapse of the mode area in higher order modes is far less than in the fundamental mode. I should mention, most of the work in the area is aimed at increasing the mode area to decrease the nonlinearity. But the other way to decrease nonlinearity is make the fiber shorter. Rather than making the fiber very large, you can make the fiber very short. And one of the examples of that is the erbium-doped phosphate fibers from MP Photonics. So when you use the phosphate fiber, you can put a lot more erbium than you can in the typical germanosilicate fibers. That lets you make the fiber very short. But our strategy has been to look at making the fiber very large. We put a number of different rare earths in these. We put ytterbium and erbium, thulium and holmium, and neodymium are also very active areas of research. We have not made higher order modes with thulium or holmium. For this talk, I'm going to concentrate on the erbium because that's the area that I'm working directly in and some that we've gotten the most results in. So let me walk you through how these large mode area higher order modes work. We come in with a single mode fiber, and then we splice to our specially designed higher order mode fiber. With this splice, we launch the fundamental mode. Then we write a long period grading, or LPG, in the higher order mode. This is very similar technology to fiber Bragg gratings, which many of you might be familiar with as reflectors in fibers, except now the grading period is much longer, a few hundred microns. And what that grading period does is gives you phase matching between the fundamental mode and the higher order mode. So it readily couples this fundamental mode to the higher order mode with very high purity, better than 99%. This is where the amplification takes place in this very large mode. And then if we want to, at the end, we add a matching long period grading to come back down to the fundamental mode and exit the fiber. So this is the waveguide design. I showed you this earlier, and it's specially designed because what we want to do is make the fundamental mode of this fiber match exactly to SMF. If we can do that, then we have very easy splicing because we have very good mode matching between the two fibers. Then we have the HOM guided it by this large outer core. We've made fibers with diameters as large as 200, core diameters as large as 200 microns. And as I said, these things are resistant to mode coupling and bend distortion, and very large area. So I like this picture because it gives a visual picture of the size of the modes that we can achieve. So standard SMF has effective areas of around 80 micron. We have some LMA fibers in erbium where we go to about 1,000 microns squared. And this is really kind of the limit for practical fabrication in these fibers at 1.5 micron. But we have HOM fibers where we've gone up to 12,000 microns squared. And this just lets us scale the peak power in these HOM fibers readily. So I'd like to say a word about mode stability. I mentioned this before, this idea of nearest neighbor coupling. It turns out if you look at the sort of perturbations that are most common in an optical fiber, bend perturbations, especially microbend fluctuations, the most common sort of coupling is between the LPON and the LP1N. So if we're operating in the LPO1 mode, it likes to couple to the LP11 mode. If we're operating in the LPO8 mode, it likes to couple to the 1.8 mode. And what we can do is for a given waveguide, we can calculate the effective index difference between these two modes that want to couple together. And as I was saying, somewhat counterintuitively, as we go up in mode order, this mode stability actually goes up. The nearest neighbor coupling becomes less likely because the modes move further apart in index. And so a stronger perturbation is required to couple them together. So, whatever mode stability proxy you want, you can always go up in mode order to get that level of stability. We've actually measured this directly with S-squared imaging. So here is a passive higher order mode fiber that we're going to operate in the LPO8. The LPO8 has an effective area of about 1,800 microns squared. So we come in with SMF, launch the fundamental mode, long period grading, then couples to the LPO8. And this is what our beam profile looks like. When we do the S-squared measurement, we can pull out these very beautiful modes. And as I was saying, one of the strongest modes is the LP18 because that's our nearest neighbor coupling. But we can actually see a number of different modes. These sort of 6-5 modes, for whatever reason, are very common in this kind of fiber. But notice the relative power levels. They're all like 20, 30, 40 dB down from the fundamental mode. So we can detect them because this is a coherent measurement, but they're very weak. But here's the important point. We sum up all the power in the higher order modes, and it's still 20 dB weaker than the fundamental mode. So less than 1% of the power is in these higher order modes. That conventional fiber that I showed you earlier, it had a much smaller area, but 10 times as much power in the higher order modes. So it was an LPO1 fiber, and the mode coupling was much stronger than this larger higher order mode fiber. So now this is what an amplifier looks like. For seed laser, we start with a narrow line with tunable laser. For the pump laser, we actually use a Raman fiber laser. We start with a ytterbium fiber laser and then use cascaded stokes to generate up to 300 watts at 1480 nanometer in the single mode. Then these two are coupled together through a fused fiber WDM, and then the amplification takes place like I was showing before. We fusion splice, launch the fundamental mode, amplification takes place in the higher order mode. This particular fiber is operating in the LPO14 and has an effective area of around 6,000 microns squared, and its amplifier length is around 4.5 meters. And the important point is this is all fusion splice, can actually be coiled to around 12 centimeter in diameter. I'm sorry, 12 inches in diameter, 25 centimeter. So these are some results on amplification of 1 nanosecond pulses in this erbium fiber. And at 10 kilohertz rep rate, we can actually get up to about half a millijoule of peak power, which corresponds to about 500 kilowatt at 10 kilohertz. The limitation here is modulation instability. This is not a limitation that exists in ytterbium. In erbium, the dispersion of the fiber is anomalous. So we have slightly different nonlinear limits in erbium than we do in ytterbium. But this is a higher order mode output, which is great. If you have some sort of application which requires Bessel beams, for example, this is a unique system which lets us generate nice Bessel beams. So you may use it for high aspect ratio drilling, for example, or people who have used Bessel beams for optical tweezing where you want to trap a line of particles rather than a single one. So there's a lot of novel things that you can do with this, but in reality, most people want fundamental mode out. So what we do here is then attach, we have a second amplifier where we've added the output LPG. Now we make this end very short. We only have about 5 millimeters of fiber after the LPG because once we've down converted, we need to immediately exit the fiber to prevent more nonlinearity. But we can do this, add this output LPG on, and it's very low loss. It doesn't significantly impact the slope efficiency of the amplifier. So here's the beam profile of the amplifier with a single LPG on it at maximum power. And here's the beam profile out of the reconverting amplifier at maximum power. And basically to the user, if the user gets this HOM amplifier, all the extra bits going on in between with the LPGs is transparent to them. All they see is single mode in, single mode out. And we can measure diffraction limited M squareds of around 1.1, so very nice diffraction limited beams. This is a slightly broader pulse. Here we're looking at 100 nanosecond pulses and getting about 1.1 millijoules out. The point here is this is now a very narrow line width system. So these systems are often limited by SBS. So we can get peak powers of 11 kilowatts in narrow line width systems. And here we're pump power limited. And finally, this is a recent result where we took this HOM amplifier and sent it to our partner Radiance, who builds erbium-based femtosecond fiber laser systems. And this is a chirp pulse amplifier. And here they operate at very low repetition frequencies. And using the erbium HOM, they were able to scale the pulse energy by a factor of 3 over their conventional fundamental mode-based system. And they achieved around sub 500 femtosecond pulses with around 300 microjoule out of the grating compressor. So in conclusion, requiring strictly single mode operation in an optical fiber severely constrains the operating design space. We want to open up the design space and enable new functionality. In general, few-moded fibers is an active area of research, and opening up the possibility gives us, to higher order modes, gives us design flexibility and fibers with properties unachievable in the fundamental mode. Thank you very much.